Hello everyone, I once again welcome you all to MSP lecture series on interpretive spectroscopy. In my last lecture, I was discussing about the influence of various factors on stretching frequency of carbon monoxide in a homoleptic as well as mixed ligand complexes. And if the metal is positively charged, what would happen is metals are reluctant pi donors. As a result, stretching frequency would be larger. On the other hand, if the metal is negatively charged, it is electron rich. To minimize inter-electron repulsion, what happens, it becomes a good pi donor. As a result, stretching frequency drops. So now let's consider analysis of more such examples here. I have listed here a series of complexes having D10, D6 electronic configuration, and this table includes both early as well as late transition metals. One fact you should remember is early metals, despite having electron deficiency, are very good pi donors. In contrast, late metals, which are rich in electrons but they are reluctant pi donors. That can be clearly seen here in these complexes of both early and late metals. If you look into D10 system having silver having a carbon monoxide group, here it is a CO compound Ag is in plus state, and here it is 22O4 centimeter minus 1, and this is much larger than the free gaseous CO, it is 2143, and that indicates again how late metals are reluctant pi donors. And if you look into nickel tetracarbonyl, again only 4 carbon monoxides are there and D10 system. Despite that, stretching frequency is quite high here, 2060 centimeter minus 1. On the other hand, in case of tetracarbonyl cobalt anion shows much less stretching frequency, nu CO around 1890. On the other hand, Mn with positive charge, MnCO6 plus, it shows 2090, and then CrCO6 is 2000, and vanadium hexacarbonyl anion shows 1860 here. So that means here, since it is manganese is positively charged, it is a reluctant pi donor. As a result, what happens? This electron density is going to the pi star of CO, and hence stretching frequency is more here. And again here, because of anion, it's electron rich vanadium, now 3d2 4s2, 5 and 6 electrons are there now. And as a result, what happens? It is a very good pi donor, and as a result, what happens? Stretching frequency drops. That means increase in electron density on a metal center, resulting in more back bonding to the CO ligands, and hence lower the stretching frequency. More electron density would then enter into the pi star orbital and weaken the CO bond. Therefore, it makes the MCO bond strength increasing and more double bond like character, with stretching frequency coming around almost ketone or aldehyde carbonyls, what we see in case of organic chemistry. This is what exactly happens here, and also I showed you in my previous lecture, it can also have something like this. Okay, now I have shown here chromium hexacarbonyl MO diagram, and here you can see this one is representing 6 sigma orbitals, sigma bonds between chromium and CO, this one, and then this is pi bonding. So pi bonding you can see here, pi star would combine with the T2G to generate a set of bonding and anti-bonding orbitals, and the bonding orbitals would occupy electrons from this T2G set. This is pi symmetry. Whereas here we are considering 6 ligand group orbitals, symmetry adapted linear combination of atomic orbitals having symmetry of A1G, T1U and EG. And now these 12 electrons would be occupying 6 orbitals, and this also you can consider as like D2sp3. D2sp3 can be seen D2s and P3. And again, valence bond theory, you can bring it here. And here that means you have a defined sigma bond between chromium to carbon monoxide, and also we have pi bond between chromium and CO. Because of this one, what happens? We have something like this happens, or I would say something like this. So this result in dropping of stretching frequency of carbon monoxide from when compared to free CO. Now let us look into nickel tetracarbonyl here. This is the nickel tetracarbonyl. Nickel having D10 electronic configuration, and then 4 COs are there. And 4 COs I have shown so many electrons here. Of course, these electrons are from 4 COs. 4 COs, if you consider, we have, this is the, so this one is responsible. So we should have 4 such lone pairs on carbon that makes them sigma donor or neutral donor towards the metal centers. If there is a metal to carbon monoxide bond is there that is held by these 2 electrons present on carbon, they are represented here. And then these 6 electrons, 6 into 4, 24 electrons would be accommodated here. You can see here. This is what I have shown here. And this one is deeply buried, so I am not showing. Now consider, from valence bond theory, we say that nickel tetracarbonyl has sp3 hybridization and it's tetrahedral. No doubt it's tetrahedral, but sp3 really involves, you can see here. And if you consider these 4 coming from here, they remain non-bonding. That means basically, and they are supposed to combine with T2 and A1 to make 4 sp3 hybrid orbitals, to which these 4 electrons should go to establish nickel to CO sigma bonds, 4 of them. But that is missing, and they remain as non-bonding. These electrons remain as non-bonding. That means in nickel tetracarbonyl, we don't have nickel to carbon monoxide sigma bond at all. Then how it is surviving? It is surviving because of back bonding. This pi star of CO combines with the T2 and E to generate set of bonding and anti-bonding orbitals, and now the electrons from D10 are smoothly transferred to this one through back bonding. So that means NiCO4 is just getting stabilized or surviving because of only back bonding. That explains why nickel tetracarbonyl compounds are unstable and highly volatile. And also you can see stretching frequency is also much higher for the same reason here. We do not have a formal sigma bond between nickel and carbon monoxide, but we have pi bond. That pi bond holds them, not as strong as we see in case of chromium, iron, carbonyl complexes, but nevertheless NiCO4 exists, but it's highly volatile compound, and readily you can dissociate CO. And this is how they made nickel tetracarbonyl to generate pure nickel through decomposition. Now I have given a list of complexes having different type of phosphines along with nitrogen donor ligands such as astronitrile and pyridine here. You can see all are derivatives of MOCO3, molybdenum tricarbonyl. 3 carbon monoxides are replaced by trifluorophosphine here, trimethyl phosphite, and triphenyl phosphine, astronitrile, and pyridine. Focus your attention towards stretching frequencies here. In case of trifluorophosphine, stretching frequencies are quite high, 2090, 2055. So this indicates not much electron density from the metal molybdenum is going towards the pi star of CO. Why it's not happening? Because there is a competition for back bonding from PF3 as well. PF3 is as good as CO in terms of its pi acceptor capability. As a result, what happens? Not much electron density goes to CO, pi star, and C triple bond is not much affected, and hence we see higher stretching frequency. But when we move from trifluorophosphine to trimethoxyphosphine, is relatively less pi acceptor in nature compared to trifluorophosphine. As a result, what happens? The stretching frequency drops here. And now, since they are not competing well with carbon monoxide, more electrons are going to the pi star of carbon monoxide in case of this compound here, and hence stretching frequency drops. That's even more pronounced in case of triphenyl phosphine. Triphenyl phosphine is a good sigma donor, but not really a very good pi acceptor. That's again reflected in the stretching frequencies of CO here. And then when you go to astronitrile, astronitrile is only a sigma donor. Now, as a result, what happens? All electron density, whatever is there from the metal, it's zero valent, that should go to only remaining 3 CO, and hence it drops further. In case of pyridine, again, it drops further to 1746 and 1888. So this gives a measure of the influence of other ligands present along with carbon monoxide on their stretching frequencies. If they are competing well, if they are good pi acceptors, their stretching frequency doesn't drop considerably, but if they are poor pi acceptor or no pi acceptors and only good sigma donors, then stretching frequency drops considerably because more and more electron density would go to pi star upon the remaining carbon monoxide. So this is a nice analogy. This can also give you some information about the position of these ligands in the spectrochemical series as well. So now what we should remember is when CO bridges two or more metals, apart from carbon monoxide acting as a terminal ligand, whatever we saw now, stretching frequencies all are of carbon monoxide acting as terminal ligands. So when CO bridges two or more metal atoms, as you see in Fe to CO9, CO bridging stretching frequency will be less. When COs are substituted by other ligands, which are only sigma donors, new CO value drops further due to more intake of metal pi electrons to pi star CO groups. That's what I showed you in my table in the last slide. In case of Fe2CO7 dipyridine, 2,2-dipyridine, for example, Fe2CO9, if you take, replace 2 carbon monoxide by a bidentate ligand such as 2,2-bipyridine, CO can act as a bridging ligand. Evidence for a bridging mode of coordination can be easily obtained through IR spectroscopy. When they are bridging, they are more or less, they are similar to ketonic carbon monoxide we see in case of organic compounds. That means they will be much less in their stretching frequency. It will be around 18 to 1700 or even less. So that clearly indicates that we have bridging carbon monoxide in a complex. So all metal atoms bridged by a carbonyl can donate electron density to the pi star of the CO and weaken CO bond. In case of Fe2CO7 dipyridine, CO stretching frequency is 2080 for terminal, whereas for the bridging one, this comes around 1850. So this also indicates how we can distinguish between terminal carbon monoxide and bridging carbon monoxide. And further drop is there whether it's if we have polynuclear or polymetallic centers, whether CO is bridging 2 metals or 3 metals, could also be gauged simply by looking into the stretching frequencies of carbon monoxide in the IR spectrum. So pi acceptor ability of CO in MCO6 place it at 0.1 to 1.2 electron per CO. That means if you consider any metal carbonyl, and carbon monoxide have a capacity to take anywhere between 0.1 to 1.2 electron density to their pi star orbitals, antibonding orbitals. That means stretching frequency decreases as more and more carbon monoxide groups are substituted, because we will be left with only few carbon monoxide to take care of electron density present in the pi orbitals. So complete substitution of CO from MCO6 has been achieved only by polydentate ligands or ligands with electronegative substituents on donor atoms having empty pi orbitals for accepting electrons. The best competitors for CO are phosphines, as I had already mentioned. Also, I showed you how it varies from PF3 to trimethyl phosphite, PPH3 like this, or PME3. So here back bonding decreases, it comes in this fashion. So advantages with phosphine is coordination properties can be readily altered. So why phosphines are more versatile compared to carbon monoxide is, no matter what happens, in order to call a ligand CO, carbon monoxide, there should be carbon, there should be oxygen, and the CO bond order can vary. Apart from that one, we cannot much do with the structure of CO. On the other hand, when you consider PR3, say PR3, by putting more electron withdrawing group on phosphorus, we can make it poor sigma donor but excellent pi acceptors. On the other hand, if you put more electron donating groups on phosphorus, we can make it very good sigma donor but poor pi acceptor. On the other hand, by a combination of these things, we can have moderate donor and acceptor properties, so that we can put them into desired metal complexes to use in some applications, particularly in case of homogeneous catalysis for organic transformations. This is where the importance of phosphines comes into pictures in their ability to control the coordination and electron saturation at the metal center in various oxidation states. This kind of unusual valency and all those things observed in case of metal complexes is because of the versatility of phosphates. Among no pi acceptor ligands. Examples are diglyme, NH3, H2O, etc. They are all not pi acceptor ligands. So mixed metal carbonyls with one or more diglyme-like ligands can also show some trends in their new CO. That means when you have only sigma donor ligands or with hard donor atoms, they can also show some trends in their stretching frequency, of carbon monoxide. For example, if you consider the stretching frequency of CO in MCO3 diglyme, which are higher than those of MCO3 diene twice. So greater electronegativity of donor, that's donor ability of oxygen. So if you consider phosphorus, arsenic, antimony, and bismuth have sigma star orbitals for back bonding. All of them have sigma star for back bonding. CO has pi star, whereas phosphines are, I would say, ER3, where E equals phosphorus, arsenic, antimony, and bismuth. They have sigma star orbitals for back bonding. So relative sigma donating ability of above donor atoms may be estimated from the stabilities of their addition complexes with AlCl3. So AlCl3 is a very good Lewis acid, so it can form readily adducts with those things. To what extent these adducts are stabilized would give some information about their relative sigma donor ability, but pi acceptor ability can be compared by making mixed ligand complexes of both carbonyl and phosphines or arsine, stibine, and bismuth compounds. The order of donor abilities follows this order here, and also in case of chalcogens, it follows this order. Of course, we call them as nitrogens also, group 15 elements. Isomers and point groups of substituted OH carbonyl groups I have shown here. This is just to identify, based on point group, how many active CO stretching bands are observed for a given geometry. For example, octahedral complexes, we can have MCO5L, one ligand is there. In that case, what happens? Your point group will be C4V, square pyramidal geometry, you can assume. The relationship of 5 carbon monoxide will be square pyramidal geometry, and you can anticipate 3 bands 2A1 plus E. And when we have MCO4L2 cis, we can have C2V point group. In that case, we can observe 4 stretching frequencies. And when it is a trans, it has a D4H, and we can get only 1 stretching frequency. And then when we consider MOCO3L3, here we can have cis and trans, that is facial and meridional. Facial will be having C3V, so we will see 2 stretching frequencies for CO, whereas meridional has C2V, we can see 3 stretching frequencies. Similarly, if you consider MCO2L4, that means the ligands are very good pi acceptor. We can have, in case of hexacarbonyls such as chromium and tungsten, we can have only 2 carbon monoxide and 4 other ligands or 2 bidentate ligands. In that case also we can have cis and trans isomers. And here it cannot be meridional, or it only cis and trans. So we can have, in case of cis, C3V, and in case of trans, C2V, and we can see here 2, and we can see here 1 stretching frequencies. So this gives some idea about octahedral complexes with substitution up to 4 carbon monoxide, what would happen, and what are the corresponding point groups. Depending upon geometric isomerism, they show cis and trans, facial and meridional. In case of trigonal bipyramidal geometry, we can have, if we replace 1 CO, we can have MCO4L, and it can be axial, it will be C3V, 3 bands. If it is radial, C2V, there will be 4 bands we can see. And again, MCO3L2, 2 axial and 2 radial, we can have D3H and 1. And when you have 2 radial, C2V, and 3 bands we can observe. And when we have 1 axial and 1 radial, we can have CS, and we can have this kind of 3 bands we can see here. And similarly, we can have MCO3L2, 3 radial and 2 radial and 1 axial but 1 radial, and we can see the corresponding point groups here. So with this table, by comparing the complexes we have on hand, we should be able to identify IR active new CO modes here. What you should do is you should write the corresponding actual structures with the geometry and try to identify the active modes, then it is easy to remember them. See, I have shown here, if we replace 1 CO, what we get is this one here, pentacarbonyl, and here it has C4V symmetry, you can see 3 bands. And then if we replace 3 of them, we can have either facial or you can have meridional, and the corresponding active IR modes for CO are shown here. And similarly, when you go for MCO4L2, we can have trans or we can have cis, whether you have C2V symmetry we have here. Here we have, so you should be able to tell here, yes, we can see only one, whereas here we can see 4 bands. Sometimes we may see 3 bands where 2 are merged or overlapped. So when we look into trigonal bipyramidal geometry, you can have all 5 are there. You can see 2 bands. When we replace one axial one, we can get 3 bands. When we put equatorial one, we can see 4 bands here. And then when we have D3H symmetry, we can see only 1 because all are in the plane. And if we have C2V symmetry, we can see 2 bands. And when you do not have any, in this case what happens, we will see 2 bands again. And similarly, in case of tetrahedral complexes, if we have MCO3L, we can see 2. And then this tetrahedral will be showing you 1. And then if you replace them with 2 ligands, ML2CO, we can see 2 bands. So this is all about mixed carbonyl complexes having other ligands. How many bands you can see, that can be determined using the point group, and then we can really identify the point group in those molecules, and we should be able to predict number of bands here. So let me stop here and continue in my next lecture few more problems before I proceed to discuss on mass spectrometry. Until then, have an excellent time. Thank you.